In this video, we're going to learn about rotations. A rotation is also referred to as a turn. But mathematically, it's considered a rigid transformation in which all points of a preimage are moved around a fixed point, called the center of rotation. Note that a fixed point does not move. And in Math 2, the center of rotation is typically the origin, which is called the coordinates 0, 0, but it can be any point on the coordinate plane. Rotations are defined by the number of degrees we rotate, the direction we rotate, which can either be clockwise or counterclockwise, and the center of rotation. When we're rotating in Math 2, we're rotating any multiple of 90 degrees about the origin, but realistically, you can rotate any number of degrees about any point you want. So here are the mapping rules for rotating 90 degrees about the origin. Notice that CC means counterclockwise, and C is the abbreviation for clockwise. So, for instance, if we look at 90 degrees counterclockwise, the mapping rule for that is xy goes to negative y, x. And so you can just use these rules with your pre-image coordinates to figure out where your image coordinates will go. Also note that if you have a number and it doesn't tell you if it's clockwise or counterclockwise, then you can assume it's counterclockwise. If you're given a negative number, like this, negative 90 degrees, that actually means you're rotating 90 degrees clockwise. So those are some things you have to remember when you're given a problem to make sure you know which way to rotate. When you're rotating clockwise, you're rotating as the clock moves, and counterclockwise is the opposite direction. If you're asked to rotate a number of degrees that's either greater than 360 degrees or less than 0, you would just keep adding or subtracting 360 degrees until you get a number between 0 and 360. So for instance, if you have 540 degrees, you would just subtract 360 degrees and you get 180 degrees. And so what that means is that if you rotate 540 degrees or 180 degrees, that pre-image will land in the same location, okay? Also, we want to talk about how you can remember the rules. So if you start here with 0 degrees counterclockwise, it makes sense that your mapping rule is xy goes to xy because you're not even really rotating, right? So those points should stay in the same location. Also, mapping rules always start with xy goes to, and so you can always write those rules. And what's interesting is the relationship between the pre-image values. So what we're doing is we're taking xy, we're flipping the sign, or we're changing the location, and then we change the sign of the first one, right? So then we take those two, we change their position, and we change the sign of the first one. We change their place, and change the sign, change their place, and change the sign. And so that's how you can make sure you have those rules, is just you're flipping and changing the sign of the first. And so those are your mapping rules for rotating any number of degrees, any multiple of 90 degrees about the origin. So properties of rotations, all points of the pre-image rotate the same number of degrees in the same direction about a fixed center point. Rotations also maintain orientation. Orientation refers to the arrangement of points relative to one another after a transformation has occurred. It can also be thought of as the order of the points when traveling around a geometric figure. Note that reflections are the only rigid transformation that do not preserve orientation. Dilations preserve orientation, and that's a type of non-rigid transformation. We know rotations maintain orientation, and translations also maintain orientation. So if you look at the example at the top right, you can see that we have 4 points. We have some type of quadrilateral, A, B, C, D. And typically when we're trying to look at the orientation, we just go alphabetically based on the way the points are named. So if we go from A to B to C to D, notice how we're traveling clockwise. So when we look at our image and we go from A prime, B prime, C prime to D prime, we're also have the orientation that is clockwise, right? So orientation is maintained. If you connect the center of rotation to any point on the pre-image and to the pre-image's corresponding image point, then the line segments are equal in length, and the measure of the angle formed is the angle of rotation. So for instance, you can see with this image, I rotated A to A prime 90 degrees counterclockwise, and then if I connect my pre-image point to the center of rotation, and then my image point to the center of rotation, it forms that 90-degree angle. we talk about mapping a figure onto itself with rotations and reflections. So when you're trying to map a figure onto itself, you can also call it carrying a figure onto itself. And when you're doing that with rotations, your goal is to determine what number of degrees will carry a figure onto itself. So something special is if you have a regular polygon. So if you have a regular polygon, you can determine how you can rotate that polygon onto itself by using the formula 360 divided by n. And I wrote that off to the side in case you couldn't read it. And n is the number of angles. If you have a regular polygon, then the number of angles and the number of sides are the same. So you could also think about this as the number of sides. Also note that a regular polygon means that the polygon is regular. And when a figure is regular, it means that it has congruent sides and congruent angles. And a polygon is just a closed-sided shape with straight sides. So a triangle is the smallest polygon. Now we will do a few example problems. So we are supposed to rotate triangle JKL 270 degrees about the origin. Remember that if you're given a positive number, it means to rotate counterclockwise. And a negative number means to rotate clockwise. So in this case, we're going to rotate 270 degrees counterclockwise. It's important when you're giving something like this to consider what location you expect your image to be in. So to do that, we actually have to plot triangle JKL first. So we have our figure drawn here. Now, if we're rotating 270 degrees counterclockwise, I can predict where I think the point should occur. So if I look at J, I know I'm moving counterclockwise, so that's moving opposite of how the clock rotates. So I'm expecting J to be somewhere in the third quadrant. And then L and K, I expect to be somewhere in the first quadrant. So when I graph my image, if I see that, then that means I'm probably right. And if I don't see that, either I made a mistake with my prediction or I did something incorrectly. So you can see that I wrote the mapping rule for rotating 270 degrees about the origin. And then I also just went ahead and wrote the coordinates next to the points. So what I can do is take those coordinates and use the mapping rule and find out where my image should be. Starting with J at 2, -1, I'm going to keep the -1 and change the 2, right? So I'm going to go from 2, -1 to -1, -2. And that's for J prime. So we have -1, -2, and that's J prime. So then I just do the same thing for K and L. K prime is going to be at 1, 1. And we expected it to be somewhere in the first quadrant, so that's good. And then L is going to be mapped to L prime, and L prime is going to be at 2, 2. So that's L prime. So we know that rotations maintain orientation, so let's just show that. If we look at our pre-image, we move from J, K to L clockwise, right? So then if we look at J prime, K prime, L prime, we should also be moving around in a clockwise motion, and we are. So that just shows you how orientation is maintained with rotations. We also heard that if you take your center of rotation, which in our case is 0, 0, and you connect any pre-image point to the center of rotation and its corresponding image point to the center of rotation, it forms the angle of rotation. So notice here, this kind of looks like a 90-degree angle, but if you go on this outside, that's your 270 degrees that you rotated. So we're trying to figure out what number of degrees will carry a circle onto itself. So if you look here, we have a circle, and that little tiny black dot is the center of the circle. So that would be our center of rotation. So because you have a circle, you can literally rotate any number of degrees, and that circle will map right back onto itself. In this case, we want to map a square onto itself by rotating. So a square is a regular polygon. It is a quadrilateral, so the 4 sides are congruent and the 4 angles are congruent. So we have to use that formula 360 divided by n. But in this case, n is 4. And so 360 divided by 4 is 90. So we can rotate a square any multiple of 90 degrees and it will map onto itself. Multiples of 90 degrees are like 90, 180, 270, 360, 540, and so on. Now we want to rotate a rectangle onto itself. So we know that all of the angles are congruent, but the opposite sides are congruent. So like not all the sides are congruent. So this is not a regular polygon, so we can't use that formula we used in example 3. So we can just use logic to figure this out. If you rotate 90 degrees, then you're going to get something like this. All right, so that obviously doesn't map onto itself. So multiples of 90 aren't necessarily going to work. So if we rotate 180 degrees, and if we rotate 180 degrees, we'll see something like this. So we can see that any multiple of 180 degrees will work. So those are like 180, 360, 540, 720, and so on. Next are the two questions that you'll be answering in the Check-in Rotations Google form. You need to determine what rotation about the origin of trapezoid QRST creates an image with point R prime at 4, 3, given the following coordinates. Q is at negative 3, 2, R is at negative 3, 4, S is at 0, 4, and T is at 0, 1. You also need to determine which of the following shapes can be carried onto itself by rotating 180 degrees about the origin. Select all that apply. This concludes our notes on rotations. These are our learning targets for today's lesson. Again, special thanks to all the people who provided the template from Slides Carnival for free, and shout out to Regents Prep for one of the pictures I used. Thanks for watching.